Hello students, in this video we'll discuss the alternating series test. The alternating series test states that if we're given a decreasing sequence of positive numbers, call that sequence an. So to be decreasing means that an plus 1 is less than or equal to an. That's the decreasing condition. Then the sum n goes from 1 to infinity of negative 1 to the an converges. So unlike our previous terms, which talk about positive terms in our summation, this series is an alternating series, can have positive and negative terms. Just as a note, oftentimes you'll see cosine of n pi used in place of negative 1 to the n. So cosine of n pi is also equal to negative 1 to the n, and so sometimes you'll see cosine of n pi in your geometric series formulas. So let's see an example of how we'd apply this. Let's show that the sum n goes from 1 to infinity of negative 1 to the n over n squared plus 4 converges. So our sequence an is explicitly given to us in this problem. So our an in this problem, so here, an is n over n squared plus 4. We need to check that this is decreasing. So if I look at f of n, which is n over n squared plus 4, and compute its derivative with respect to n, we have that f prime of n is equal to the bottom, n squared plus 4, times the derivative of the top, which is 1, minus the top, n, times the derivative of the bottom, that's going to be a 2n, all over the bottom squared. N squared plus 4 quantity squared. So now what we see is if we simplify this, we'll have an n squared plus 4 minus 2n squared, all divided by n squared plus 4 quantity squared. So if we simplify this, we're going to have a 4 minus n squared all over n squared plus 4 quantity squared. And we see, however, that if n is equal to 1, this is positive, and if n is equal to 2, this is equal to 0. So for n equals 1 and n equals 2, this term over here is bigger than or equal to 0, so it's increasing initially. But once n gets past 2, the series is decreasing. So f of n is decreasing if n is bigger than or equal to 3. And we know from our study of series that it doesn't really matter where the series starts as long as a property is eventually true, so i.e. f is always eventually decreasing, we can apply the alternating series test. So it's decreasing for a certain range, therefore the series converges by the alternating series test. Let's see another example of this. So now we can construct all sorts of sequences that have this property. So for example, just one other quick example. If I look at the sum, n goes from 1 to infinity of, let's put cosine of n pi over here. As we noted above, that's the same thing as negative 1 to the n. So this is an alternating series. And then if we do something like this, if we have an n e to the negative n, we can see that this series will converge by examining this sequence n e to the negative n. So if we look at n e to the negative n, and I compute its derivative with respect to n, we'll have the first function times the derivative of the second function, and then the second function derivative of the first. So if we factor this out, what we're going to see here is we're going to have an e to the negative n And then if I do that, I'm going to have a 1 minus n. And we see that if n is bigger than or equal to 1, that this will be negative. So in fact, this sequence, n e to the negative n, is decreasing, so therefore this series will converge by the alternating series test. So whenever we have an alternating series, we examine the terms that do not contain a negative 1 to the n, and we'll take their derivative. If their derivative is eventually negative all the time, then the series will converge by the alternating series test. Thank you very much.